Hello everyone. Today we'll study carboxylic acids and its derivative. Now this chapter, since it has come after many chapters, definitely reactions are going to repeat in this chapter. Most of the reaction that we'll be seeing we have already covered somewhere in other chapters, as the method of preparation in this chapter will be reactions of other chapters. The reactions of this chapter would be method of preparation of some other chapters. So you'll be very friendly, you'll be very familiar with many of the reactions that we are going to see today in this chapter. And so this chapter will be covered pretty fast because the reactions will be covered pretty fast because reactions will be pretty familiar. Alright, to start with, let me introduce this chapter to you. In this chapter we'll study about carboxylic acids. Carboxylic acids you know from many years. Carboxylic acids look like this. This R group can be aliphatic, aromatic, whatever. Basically, you have many reactive sites. To identify the first reactive site, of course this hydrogen, because this hydrogen in this bond, the electrons are more shifted towards oxygen, so this hydrogen is having plus charge polarity, this oxygen is having negative charge polarity, and we have seen million times, I have told you, reactions are nothing but electronic exchange. So basically the site which is electron rich, from there the electronic exchange will start. Electrons will be poured from that site, and the site which is electron deficient, they will be at the receiving end. So reaction will be at both the ends, whether it is electron rich or whether it is electron deficient. To identify reactive sites, you just have to identify electron rich site and electron deficient site. So we have identified two of the reactive sites. This carbon though is not much of the reactive, because this thing we have done based upon electronegativity difference. As we know, there will be resonance here. So this oxygen will be giving its electron into the orbital of this carbon to develop a partial double bond here. So this oxygen is basically electron deficient if you draw the resonating structure of this. When you draw the resonating structure of this carboxylic acid, you will have the structure like this. So in the hybrid, there will be characters of both the resonating structures. Here this oxygen is neutral, here the oxygen is having +1 charge. So in the hybrid, actually this oxygen will having some plus charge polarity because of resonance. So this oxygen is not the reactive site that we are looking for. Come to this carbon. This carbon, because of electronegativity difference, this oxygen will be pulling some electron, much of the electron from this carbon away. So this carbon will tend to have a plus charge polarity, though there is a plus M effect of this oxygen, and because of that the plus charge polarity will be mitigated, but still there will be some plus charge polarity. So nevertheless this will be one of the reactive site. Then we can see C double bond O. This C double bond O can be another reactive site for addition of any reagent like hydrogenation, although this is not a pure C double bond O because of this resonating structure, and in this resonating structure we can see there's a single bond. So there's only a partial double bond character at this position, but a strong reagent can get added at this position. Then another reactive site is this bond. As we have seen one of the reactions previously, that is decarboxylation. In decarboxylation we have seen that the CO2 is removed off and you have a negative charge on this carbon. So we can have another reaction in which whole of the R group will be participating. Whole of the carboxyl group will be participating, and in that kind of reaction whole of the carboxyl group will leave the substrate and this bond will be broken, consequently forming a negative charge on the carbon. So this bond is again a reactive bond, and this is one of the reactive site, and we'll see the reactions at this site as well. If I open up this R to show you the alpha carbon and alpha hydrogen, suppose let me write it like this, RCH2. The next reactive site is this carbon. Now this carbon being at the alpha position of the acidic group, this carbon is at the alpha position. That means if I remove hydrogen out of this carbon, a negative charge that will develop on this carbon can do resonance with this C double bond O. Although there is a cross conjugation, that means this carbon is having the source of electron from both the sides. If I remove hydrogen from this position, then the negative charge will be developing on this carbon. So this negative charge will tend to do resonance with this C double bond O. But this C double bond O also has availability of electron from this oxygen. So basically electrons from both the sides will rush to fill the empty orbital of this carbon. So because of that, the carbon will be having electron from both the sides. So tendency to have electron from one of the side will drastically decrease. So this acidic group do not have any minus M effect as we have seen earlier. But still, nevertheless, there will be some extent of resonance, so there will be some stability of this C negatively charged carbon by mesomeric effect, minus M effect, plus there is a huge, very high inductive effect of this carboxylic acidic group because of two electronegative atom present. So because of inductive effect and because of slight resonance, this negative charge will be stabilized. So the hydrogen at this position can also be removed with ease. So this is also one of the active hydrogen apart from this hydrogen. So this is another reactive site. So first what we'll do is we'll start to study the method of preparations, and we'll see that all the method of preparations we have already seen. Next we'll catch up with the reactions of this carboxylic acid, and again we'll see most of the reactions we have already seen. So basically it will be a recapitulation of the reactions done in previous chapters, but we'll arrange things, preparations and reactions in proper order. So this thing will retrieve back to this discussion once we get started with the reactions of carboxylic acid. First of all, let's complete quickly the method of preparation of carboxylic acids. The first method of preparation is as old as about 4 years maybe. You may be knowing this reaction. Aldehydes get converted to carboxylic acid very easily. Any weak oxidizing agent is able to oxidize aldehyde to carboxylic acid. So oxidation is one way to get carboxylic acid out of aldehyde and some other functional groups as well. But in case of aldehyde, you get carboxylic acid with greater ease. When you have aldehyde and when you have oxidizing agent, and this nascent oxygen will be produced from that oxidizing agent, whatever you will take, and this nascent oxygen will get inserted between carbon and hydrogen very easily, and that will result in formation of carboxylic acid. Now this technology of insertion of nascent oxygen is not available with ketone with so much of robustness and greater ease, because in ketone you have a bond between carbon and carbon, and that carbon and carbon are stronger or bigger atom than hydrogen. So the bond between carbon and carbon is stronger than between carbon and hydrogen. So the insertion is difficult than it is in case of carbon and hydrogen. So this insertion is very easy. Any oxidizing agent can do it. This insertion is difficult. So weak oxidizing agents like Tollens reagent, like Phelan solution, like Benedict solution will not be able to oxidize ketone. They'll be able to oxidize aldehyde. So there will be no reaction unless you're having a very strong oxidizing agent. And in case of ketone, you must have strong oxidizing agent like hot KMnO4 in acidic medium, or you may have potassium dichromate as well in acidic medium. In acidic medium, what happens is the higher oxidation state tends to be less stable. Like if you look at manganese in potassium permanganate here in KMnO4, the oxidation state of manganese is +7. That's very high. When you add acidic medium, then magnesium tend to come at lower oxidation state. In fact, manganese comes at lower oxidation state. It comes to oxidation state +4. It forms MnO2. In MnO2, manganese has +4 oxidation state. In KMnO4, it has +7. So oxidation state has decreased. That means it has gained some electron. So in turn, reduction of KMnO4 has taken place. So in turn, someone has to get oxidized, and that someone is this ketone. This ketone gets oxidized to form carboxylic acid. So you do get carboxylic acid in oxidation of ketone, but for that matter you require a stronger oxidizing agent, and we are taking hot. When it's hot, then the reactivity is higher. For that purpose we take hot KMnO4. So you get carboxylic acid in both the cases. But in ketone, I mean, because of this extreme condition, there can be oxidation at some other end as well, apart from these two bonds. Other ends of this R, if there's a alkene, if there's unsaturation in this R part, then that alkene can also undergo oxidation, resulting in another acidic group. So this is unreliable. We are not sure that oxidation will take place only at this end. Other part of R can also get oxidized in this extreme condition when we take a very strong oxidizing agent, and that too hot. So this is not a good method of preparation, but nevertheless, if you have oxidation, you will get carboxylic acid. So this is one of the method of preparation by oxidation of carbonyl compound. So these were carbonyl compounds. You have aldehyde and ketone. When you oxidize aldehyde and ketone, you get carboxylic acid. That's one way of doing it.